Yeah, beta. In previous class we completed about the boron family, even the compounds of the boron and all. Now the same topic, that is a P block of first year, and in this P block of first year, beta, we have to go with a fourth A group element. So this fourth A group element is called as the first element will be a carbon, so it must be called as a carbon family. But in this one, what are the elements present on that? Carbon, silicon, germanium, tin, and lead. But if you know the atomic number of one element, we can write the atomic number of other element by knowing its a magic number. Right, beta? So by knowing the magic number, we can write here. Silicon, beta, it become a what? 14. Because 6 plus 8. Then germanium. You know germanium is coming on which group element? So it comes on the 14th group element. 14 group. Zinc is a 30. But zinc will come as a 30. After zinc, we are getting here as a 1 second, beta. After the zinc, right, beta. That means carbon, silicon, germanium, tin, and lead. After that one, beta, if you see the germanium, actually it is coming what before gallium, and gallium is coming what, that is a after the zinc. Zinc 30, gallium 31, then it should come as a 32. Actually, what we did, beta, here 14 to 32 means we added 18. 8 plus 4, 12, carry 1, 32. And here we added 8. So 8 plus 18 plus 18 plus 32. These are the number we have to add. We'll get atomic number. 32 plus 1 more 18, beta. By 18, 30, 40 and 50. 50 plus 32, it become a 82, their atomic number. And if you write their configurations, you know, it will come as a helium, then neon, then argon, then krypton, then xenon. 1s2, right, beta? 1s2, 2s2, 2p2, 2, 4 plus 2, 6. It become a 3s2, 3p2, 10 plus 4, 12. Beta argon, 18th. 18 plus 2, 20, 20 plus 10, 30, 30 plus 2, 32. Then 5s2, 4d, 10, 4, 5p2, 5p2. Sir, it is a 6s2, 4f14, 5d, 10, 6p2. See, beta valence 6s2, 6p2, 5s2, 5p2, 4s2, 4p2, 3s2, 3p2, 2s2, 2p2. Means general electronic configuration of this group element is what? NS2, NP2. That means you can see, beta, in p orbital we have 2 electrons, and in s orbital we have 2 electrons. Means this group element, that is a M of this group element, has a tendency to lose 2 electron and as well tendency to lose remaining 2 plus 4. So they are having a variable oxidation state or variable valency of plus 2 and plus 4. In NCRT they wrote the same thing, beta, about the trends in the oxidation state. That part we are going to learn in trends in the oxidation state, right? So in this case now I am going to discuss with you. The first one is electronic configuration. So first one I want to discuss electronic configuration of this group element is NS2 and P2. Second one, so what about their radii, covalent radii? Obviously these have a tendency to form the covalent bond. So we can say the covalent radii. For this case, it is increases down the group. But as we are coming down the group, atomic size increases. How? You can see 2s2, 2p2. That means second shell, then third, then fourth, then fifth, sixth. As we are coming down the group, you are differentiating electron. But the last electron, beta, it enters into new shell. In this case, it enters on second, then it entered on third, then fourth, then fifth, then sixth. As we are coming down the group, beta, electron enters into the new shell. As the electron entered into the new shell, their atomic radii or covalent radii increases. Is it clear, beta? Right. We can go with the ionization energy for this group element. Nothing is there. Say for ionization energy, but as we know that ionization energy is inversely proportional to atomic radii or covalent radii, and as we know that while coming down the group, covalent radii increases, so obviously ionization potential value decreases down the group. Decreases down the group. But in NCRT, if you want to see here, the first ionization energy of the 14 group member will be higher than the corresponding member of the 13th group. Obviously, beta, because as we are going from 13 to 14, atomic size decreases. As the atomic size decreases, beta, as the atomic size decreases, here we can say about now. Example I will show you. Sir, this is a group 14th element, and this is a group 13th element, and this is a group 15th element. Obviously, what we can say, as we go along the period, atomic size decreases. As we go along the period, atomic size decreases. Atomic size decreases. Now compare the 13 group with the 14 group. What is that? 14 group will have a smaller atomic size than that of 13 group. So smaller the size, greater the ionization energy. So I can say here, if we compare group 13 and group 14, for the ionization energy, smaller the size, greater the ionization energy. May I correct now, beta? Along the period, atomic size decreases, ionization energy increases. Hence, the first ionization energy of group 14, shall I write beta here? IP1. IP1 of the group 14 will be greater than the IP1 of the group 13. Again, as we are coming down the group, f orbital involvement is there. F orbital does not provide good shielding. Again, atomic size get decreases, ionization energy increases, but that is due to the poor shielding and all, or due to the lanthanide contraction. We can see that part. But the next part of this one, we'll see the after this covalent radii ionization energy, we'll talk about the electronegativity. Right? The fourth point I want to write here. Fourth point, sir, electronegativity. As we are coming down the group, atomic size increases. As the atomic size increases, electronegativity value decreases. Right? We don't have much variation about the electronegativity value. Here, electronegativity value for the element, carbon, silicon, germanium, tin and lead. If you see for the carbon to silicon, silicon to germanium, means if you want to see here, silicon to lead, from here to here, silicon, germanium, tin and lead, but these elements are having a nearly almost same electronegativity value. They are having almost same electronegativity values. So this is about the properties, or we can say general properties of 14 group element. But next of this one, we'll go for the next topic, that is a physical properties of this group element, how it will be. Chalo, I will go with the physical properties. Carbon, silicon, germanium, tin and lead. Physical properties. Sir, they have a tendency to lose 4 electron. As they have a tendency to lose 4 electron, they can or has a tendency to gain 4 electron. Means it may behave as a metal as well as non-metal. So it will come under the property of what? Metallides. Carbon, silicon, germanium, tin and metal, this group element has a tendency to form the semiconductors. Means we can see here, all the elements of group 14s, they are the solid. Right, beta? They are the solid. Even carbon, silicon, if you want to compare, they are how? Carbon, silicons are the non-metals. Germanium, you can count here, beta. Physical properties, I will tell you. Physical properties of these group elements are carbon, then silicon, then germanium, then tin, and then lead. Sir, this is a metal, right, sir? But it is a metal. Carbon, silicon, sir, they are the come under the part called as a non-metal according to NCRT, beta. Right? Germanium is a metalloid. Tin and lead are the soft metal. Here, this is the metalloids. Metalloid. Tin and lead are the soft metal. Right? So as we are coming down the group, metallic nature increases. So as they are having the soft metal means they must have a low melting point value. They are having their melting point value will be very low. So low melting point value. But a melting point and boiling point value of 14 group element will be higher than the corresponding 13 group. Yeah. If you compare group 13 and if you compare Group 14. Compare the MP and BP value of these two. But it was seen that melting point and boiling point value for 14 group element will be higher than the 13 group, right? Due to smaller the size, smaller the bond length, greater the bond energy, higher the MP and BP. This is about the physical properties of 14 group element. But the next one is chemical properties now. Next one we'll see now chemical properties. But the most important part in the chemical properties is oxidation state. 14 group element are having a variable oxidation state of what? +2 and +4. हाँ बेटा just now we saw ना. It has a variable oxidation state of what? +2 and +4, right? So that part only I'll discuss. Chemical properties. But in IIT exam, NEET exam, in MCET exam, in all the competitive exam, this part definitely they will ask from this one. What is that? Oxidation state. Sir, oxidation state and its trends in the chemical reactivity. Sir, as we know that fourth A group element are having a general configuration of NS2 NP2. That means they must have a variable valency of +2 and +4. But we know that as we are coming down the group, as we are going down the group, stability of +2 increases. And why it is increases beta? Due to inert pair effect. Sir, what is the inert pair effect? Beta, electron present in the s orbital does not participate in the bond formation. Means whatever the electron present in s orbital cannot easily involve in the bond formation. At the same time, sir, we can say again, sir, down the group, stability of +2 increases down the group. What about +4 beta? Yes, +4 decreases. So stability of +2 increases and stability of +4 decreases. Let me give one example for you here. One example I want to show you. Sir, what is the last element in this group element? Carbon, silicon, germanium, tin and lead. See beta, take the example of PB. So it was seen that PB ka +2 will be more stable than +4, and this is the stability of oxidation state. Reason is what? Sir, same. It is due to what? Inert pair effect. But in exam, IIT exam or in NEET exam, for this concept, they can ask you, if it is more stable, that means your reaction should move from PB +4 to PB +2. How the +4 become +2 beta? By gaining electron. That means it has a tendency to gain electron. PB +4 can undergo where, sir? Reduction. But as a PB +4 can undergo reduction, that means our PB +4 will act as an oxidizing agent. They can ask you among the following, which one will can act as an oxidizing agent or reducing agent. Sir, it can be explained based on less stable to more stable. PB +4 is less stable and our reaction has to move from less stable to more stable. How it will move from less to more? By gaining 2 electron, it forms PB +2. Means it has a tendency to undergo reduction. It must act as an oxidizing agent. What beta? About the PB +4. So once again, I will repeat here what we have seen in the oxidation state beta. 14 group element. That means this group 4, fourth group element carbon family. They are having a variable oxidation state of +2 and +4. Carbon also exhibit the negative oxidation state beta. +4, -4 both are possible. But it was seen that the compound with +4 oxidation state are generally covalent in nature. That point I didn't discuss with you, but I will tell you. If any compound is there and compound it is in +4 oxidation state, the nature of the compound is a covalent nature. But these things maybe you have learned in chemical bonding, Fazan's rule. According to Fazan's rule, what is that beta? Cation will have the greater charge on the cation, that is smaller the size. Greater the charge on the cation, smaller the size of the cation, greater the polarizing power, greater the polarizing power, greater the covalent character, right? That's why they are saying if the compound in is +4 oxidation state, the compound formed by that element in +4 must be a what? Covalent in nature. But a heavier member of this group element like a Pb, lead, sir, it will be more stable in lower oxidation state due to what, beta? Due to inert purified. Means if you want to see the oxidation state order for this one, it was seen that I will write, beta, germanium, tin and lead. It is the order of stability of +2 oxidation state. Lead will be more stable than tin than germanium. That means what about germanium, beta? Germanium will be more stable in the +4 oxidation state. So this concept is there not to explain the germanium concept. I will take one more example. Please take a note or take a screenshot of this part, beta. Is it clear, beta? Chalo, I want to show you here itself. Now, Pb is more stable in +2. We wrote here Pb is more stable in +2 than +4 because as we are coming down, the group stability of +2 increases due to inert pair effect. So lead will act as an what? Oxidizing agent. But lead will act as an what? Oxidizing agent. Come for the germanium. But a germanium can form the compound +4 and +2, but it was seen that germanium +4 will be more stable than +2. How it? Because oxidation see stability of +2 increases, stability of +4 decreases. Na? That means germanium become more stable in the +4 oxidation state. Germanium become more stable at the +4. But some compound of germanium, they will be more stable at the +2 also. Right? Tin is there. Come for the tin, Sn. Here. Tin, Sn. But Sn has a compound in +2 as well as +4. They didn't talk about the stability of the tin and all. Germanium की stability they talked here. But if germanium is more stable in +4, so how the reaction should move? Germanium +2 by losing one more 2 plus electron, so it underform the +4. That means we can say germanium +2 has a tendency to lose electron, so germanium +2 must undergoes oxidation. But any ion which undergoes oxidation must act as what, beta? It must act as reducing agent. Remember, germanium +2 reducing agent, Pb +4 oxidizing agent. Okay, note down. But what we can say now, oxidation state and all. In this one, we have seen that the heavier element of this group are more stable in the lower oxidation state, but germanium will be more stable at the higher oxidation state. Right? They are having the variable oxidation state of what? +2 as well as the +4. But not only that, with this oxidation state, we can talk about the electron precise molecule can be formed by this group element. With this one, okay, we can say. So carbon has a tendency to form the +4 oxidation state. That means this is the first part. Carbon does not have vacant orbital, but due to the absence of the vacant orbital, it has a tendency to form a electron precise molecule. But species, these electrons, or we can say there is a three different type of the compounds are there. One is electron deficient, one is electron rich, and one is electron precise. So here carbon has a tendency to form a electron precise molecule. But an electron precise molecule means central atom have only 8 electron in its valence shell. But having the 8 electron in the valence shell will make it as a what? Stable. Hence, electron precise molecule example is that you can say carbon tetrachloride, or you can say carbon with a 4 hydrogen, or we can say CCl4. But due to the absence of vacant d orbital, we can say compound of carbon, right, CCl4, it does not undergoes hydrolysis. Sir, why it does not undergo hydrolysis? But for undergoing hydrolysis, central atom must have vacant orbital. So compound of carbon like CCl4 does not undergo hydrolysis. Reason is due to absence of habita, due to absence of vacant d orbitals on where? On central atom. At the central atom does not have any vacant orbital, it cannot undergo hydrolysis. So what we can say, beta, the maximum covalency of the carbon must be 4, because due to absence of vacant d orbital it cannot expand, it's octet. But other compound, let me tell you here only, but other element of this group element have a maximum covalency is equal to how, beta? They have a tendency to expand their octet, and they can have their maximum covalency up to 6. For example, I'll tell you maximum covalency equal to 6. Example, beta, after carbon, what is that? Silicon. It has a tendency to form SiF4 2 negative ion. Because silicon is having a vacant d orbital, has a tendency to gain electron. Germanium, yes sir. How about germanium? Yes sir. It also has a tendency to expand their octet. But a tin, yes, it also has Sn. What is that? OH taken 6 times 2 negative ion. So they all are having a maximum covalency of 6. Did you got? But in this one, hybridization of the central atom can be changes. Here you can check, beta, CCl4 or CH4 mein hybridization of carbon atom is what? Only sp3. But in all the cases, either silicon or germanium or tin, the central atom ki hybridization you can check, beta. For getting the Z value equal to 6, the hybridization should come as a what? sp3d2. So the central atom must undergoes sp3d2 type of the hybridization. So d orbital involved in the hybridization. So it is a first point, or the we can say the important chemical properties of oxidation state and trends. Now we'll see the reactivity of this group element towards the oxygen. Please take a screenshot, beta. Right. So reactivity of this group element toward the oxygen. How this group element can react with the oxygen? But when these group elements are combining with the oxygen, they have a tendency to form two type of the oxide. What is that? So one is a monooxide and other one is a dioxide. Right, beta? The reactivity of this group element with the oxygen. So reactivity towards oxygen. This group element M, that is a fourth A group element, on combining with the oxygen had a tendency to form this oxide MO and MO2. Yeah, but two type of the oxide. What is that? MO, and other one is what? MO2. Any doubt beta in this one? These are the two oxides formed by 14 group element. So what is the MO and what is the MO2, beta? Beta, MO is a monooxide and MO2 is a what? Dioxide. Is it clear, beta? How? Check it here. Sir, M ki valency plus 4. Oxygen ki valency 2 minus. Beta, 2 ones are 2 twos are. What is that? MO2. So this must be called as a dioxide. If it is a dioxide, then it should be what, sir? Monooxide. So 14 group element has a tendency to form what? Two type of the oxide, dioxide and monoxide. But example I'll say silicon oxide. I'll say give an example. This is example given in our NCERT, beta. SiO. But SiO only exists at high temperature. It only exists at high temperature. But oxides in the higher oxidation state of the elements are generally more acidic. Check it here. What is the oxidation state of this metal? Sir, +2. Beta, what is this? Sir, +4. So I should say dioxides are more acidic than monoxides. Why? Because dioxide will have a higher oxidation number. Greater the oxidation number on the element, greater its acidic strength. So I can say among the monoxide and dioxide, dioxide will have +4 and monoxide will have +2. So dioxide become a more acidic than the what you can say monoxide. Now example I'll show you. Dioxides के example. Sir carbon का dioxide CO2. Silicon का dioxide बेटा SiO2. कार्बन सिलिकॉन जर्मेनियम का डाइऑक्साइड GO2, right beta? They all are what? Acidic in nature. See here, they all are what? Acidic in nature. Beta, what is the next one? Carbon silicon germanium. Beta, tin का डाइऑक्साइड SnO2. Then lead का डाइऑक्साइड PbO2. It is given in your NCERT also. Sir, they are what? They are amphoteric in nature. The first three are acidic, next two are amphoteric. Got the point? Come for the monoxide के examples बेटा. Monoxide का example CO. Sir, how the nature is? Very good, sir. Neutral. CO बेटा neutral. GeO distinctly acidic. Distinctly acidic. Now remaining two, what is that? SNO, PbO, amphoteric. But IIT mains, NEET, even MSET, we are getting this question. This question, among the following, which is a neutral oxide? CO. Among the following, which is an amphoteric? SNO, PbO, amphoteric. SNO2, PbO2, and but a tin and lead, either it is a mono or it is a di. Nature is amphoteric. But dioxide make carbon, silicon, germanium is acidic. But here only carbon is a neutral. Remaining GeO, that is a germanium oxide. What we can say? They are the distinctly acidic in nature, right? Sir, why you didn't wrote the SiO? Beta, it is exists only at the high temperature, and definitely carbon silicon mein aisa, if you want to say, it also have a very little property of the acidic in nature, but I don't want to discuss anything about that. NCERT never says about the nature of the SiO, so I didn't discuss. He discussed about neutral, distinctly acidic, remaining two amphoteric, these three acidic, these two amphoteric. I given the discussion of that one. Right, take a screenshot, sir. So most acidic oxide, right? Most acidic oxide, right? But a +2 oxidation state, most stable +2 oxidation state, Pb+2 will be more stable, right? But among these one, which element will be used as a semiconductor? Silicon and germanium will be used as semiconductor. But these are the point was given in the NCERT curriculum. I have given for you. Remember, very important point. Even in exams also they are asking us. So next one we'll go with reactivity towards water and then reactivity towards halogen. So now we'll check it the first reactivity towards water. How this element can be reacting toward the water. So reactivity towards water. But you know these first three elements, carbon, silicon, germanium, they are not affected by the water. These three, carbon, silicon, germanium, they are not affected by the water. But The decomposition stream was there. Na? Suppose tin you take it here. Tin and a carbon, silicon, germanium. Next one is tin. And next one is better lead. But a tin kile, just you pass the steam over it. That means on heated at a very high temperature, it will be decomposes the water and form its oxide and liberate the hydrogen gas. Khatam. But it liberate the what? Hydrogen gas. 2 2s are 4, make it 2, and it form SNO2. But a lead is there. Lead, Pb. It is unaffected by the water. Why? Due to the formation of a protective oxide layer. Lead is also unaffected with water. Sir, why the lead is unaffected with the water, beta? Due to the formation of a protective oxide layer on its surface. Due to formation of oxide layer on its surface, means among this group element only Sn is there. It can be affected with the water, that to be at very high temperature. Remaining 4, carbon, silicon, germanium and lead are unaffected with the water. Right? Note down this one. Then reactivity towards halogen, beta. Reactivity towards halogen. Very important. Huh? It's a very important concept. This group element on combining with a halogen to form their halides of the formula M की valency plus 4, halogen की valency minus 1 and form the MX4 type of the halide. But it has a tendency to form 2 type of the halide. Sir, reactivity, but a reactivity towards halogen. Sir, reactivity towards halogen. But these group elements are there. They have a tendency to form the 2 type of the halide. Let me tell you, this M is a 4th A group element. On combining with X is the fluorine, chlorine, bromine and iodine. And it has a tendency to form 2 type of the halide, MX2 and MX4. Sir, called as a dihalide, and this is called as a tetrahalide. Yeah, beta. This group element has a tendency to form 2 type of the halide, dihalide and tetrahalide. But except carbon, all other member react directly with the halogen. Here, if you want to talk about the carbon, na, so except carbon, all other elements directly combine with a, yes sir, they can directly combine with halogens. That means carbon cannot combine directly with the halogen and it cannot form its halide directly. Got the point? So all other members can react directly with the halogen under suitable condition to form the halide. But among these one, if you want to talk MX2 and MX4, it was seen that, sir, our MX4, the compound is a covalent halide formed by this 14th group or a 4th group element. But a central atom of this metal or element, not a metal, sorry, beta, this central element or central atom, it undergoes sp3 type of the hybridization, and the molecule will have what? Tetrahedral in shape. Obviously, beta, it has a what?